I'm Anuj Dawar, and I'm here with my colleagues and collaborators, Benedikt Pago and Tim Seppelt, and we will talk you through this paper. So we're working in the realm of algebraic complexity. Algebraic complexity is concerned with computing polynomials. So here, consider a polynomial over a field F with variables from the set X. And what we're interested in is how many operations of addition and multiplication are needed to compute this polynomial. For example, consider the polynomial, very simple, in two variables, x plus y squared, which can also be written as x squared plus 2x plus y squared. And these two ways of writing it, for example, represent two different ways of computing the polynomial. On the left, we add x and y first, and then multiply the sum to itself. And on the right-hand side, we multiply x with itself, y with itself, multiply x, y, and 2 together, and then add the three things. So you see that the version on the right requires, in principle, more operations, 3 multiplications and 1 addition, while the version on the left is 1 multiplication and 1 addition. And we're really interested in minimizing the number of operations needed, or working out how many are needed. Of course, mainly we're interested in the asymptotic growth. So it's the complexity of a family of polynomials rather than of a single polynomial, typically indexed by n, which might be the number of variables. We want to know how this grows with n. The kinds of polynomials we're interested in are usually polynomials where the variables are the entries of a matrix. So the set of variables x has a certain matrix structure to it. So we can think of it as the set of variables xij indexed by I ranging, let's say, from 1 through m and j 1 through n. An example where m is equal to n, very common, is the determinant. So the determinant of an n by n matrix can be written as a polynomial, and here is a sort of its definition. It's the signed sum of these permutation monomials. This is a exponential size expression, but there are smaller expressions for computing the determinant. And another classic one we consider is the permanent. So the permanent of an n by n matrix looks just like the determinant, except we've dropped the signs. So it is the unsigned sum of the permutation monomials. And here again, this expression is of size n factorial. We can do better than that, but the only known expressions we have are still of exponential size. I've just said this. The determinant can be computed by polynomial size algebraic circuits. And Veliant's conjecture that Vp is different from Vnp, sometimes called the algebraic equivalent of the P versus Np question, is equivalent to saying that the permanent cannot be computed by polynomial size algebraic circuits. To establish this conjecture, people have looked at establishing lower bounds on the complexity of the permanent, and while general lower bounds are out of reach, people have looked at restricted notions of circuits to try and establish lower bounds, unconditional lower bounds for restricted notions of circuits. And one of the earliest results along this line is by Jerem and Snur, who showed that no sub-exponential size family of monotone circuits computes the permanent, where monotone here means that all constants that appear are non-negative. So this, of course, is specifically over the real field. There's also results for bounded depth circuit. For instance, no sub-exponential size family of depth 3 circuits computes the permanent, and this works over any field, I believe, or any finite field. It turns out that both methods yield similar lower bounds for the determinant. So I say similar because, the determinant is not itself a monotone polynomial, so one has to qualify this somewhat. But what this is really saying is that in some sense, the lower bounds we get tell us not just about the hardness of the permanent, they also tell us about the weakness of the model, because the determinant is, in principle, an easier polynomial, but we have exponential lower bounds in these models. Another notion we consider, and which is sort of the motivation for our present work, is this result, which appeared in a paper of mine with Gregory Wilsonak, where we showed that no sub-exponential size family of symmetric circuits computes the permanent. I will explain what this notion of symmetric circuits is in just a moment. And here, by contrast, there are polynomial-sized symmetric circuits for computing the determinant. So this actually provides an exponential separation between the permanent and the determinant, and is in one sense what makes this notion of symmetric circuits so interesting. So let me explain the notion of symmetry. I looked at a polynomial x plus y squared, Now, in this polynomial, if I interchange the two variables x and y, the polynomial remains unchanged. It's exactly the same. So the polynomial is invariant under this permutation. The two circuits we saw before are symmetric in the sense that if I exchange the variables x and y at the inputs to the circuit, I can extend this to a permutation of all the gates, which leaves the circuit unchanged. So here is the example of the second example of the circuit. So if I exchange the variables x and y, I can also exchange the two multiplication gates on the left-hand side and the right-hand side with each other, leaving the other two gates fixed, and that is an automorphism of the circuit. It leaves the circuit unchanged. There are other ways of computing this polynomial. Here's another example. It still computes the same polynomial, but this one is not symmetric in the sense that interchanging here x and y, there is no automorphism of the circuit, which you can easily see because this gate, the multiplication gate, has two inputs, both from the variable y, but there is no gate with two inputs from the variable x, right? So there is no permutation of the gates, which will leave this unchanged while exchanging x and y. So the left-hand side is a symmetric circuit for computing this polynomial. On the right-hand side, we have a circuit which is not symmetric. So more generally, suppose you have a permutation of the variables x. Say that a circuit C is symmetric with respect to this permutation. If applying this permutation to the variables extends to an automorphism of the whole circuit. Still more generally, we say this for any subgroup of the symmetric group on X. We say that a circuit is gamma symmetric if it's pi symmetric for every permutation in gamma. When the set of variables forms the entries of a matrix, which is, as I said, the case we're interested in, we're particularly interested in a subgroup of sim X, which is what I call the group SM times Sn. So the direct product of permutations of the rows and the permutations of the columns, where the action is defined by any element of gamma takes the variable xij to x pi I sigma j. All right, pi sigma takes xij to x pi I. So you permute the rows according to pi and the columns according to sigma. And the theorem that I mentioned before about symmetric circuits essentially says that there is no sub-exponential size family of gamma symmetric circuits for this particular gamma for computing the permanent, right? There's an unconditional exponential lower bound on symmetric circuits for the permanent. Okay, I'm going to hand over to Benedikt to take over from here.
Yeah, so I was trying to extend this symmetric circuit lower bound and prove lower bounds for other polynomials than the permanent. But this turned out to be quite tricky. So the precise methods that work for the permanent didn't seem to work out for other matrix symmetric polynomials. And I thought about this for a while, and then at some point I realized that maybe there's a different way to approach this whole problem. Namely, you can see that all matrix symmetric polynomials in fact express subgraph counts. So what I mean by this is, for example, here, if you look at this matrix symmetric polynomial, then, so this is the sum of all degree 2 monomials where the second index is the same in the respective variables and the first two indices are different. And you can now think of each of these monomials as representing this graph that you see at the bottom, this path. So each variable corresponds to an edge, and then every index tells you where the end vertex of the edge is being mapped. So this is like an enumeration of all possible embeddings of this three vertex path into an unspecified bipartite graph with 3 vertices per side of the bipartition. So if you evaluate this in a concrete biadjacency matrix of a bipartite graph, it will tell you exactly the number of occurrences of this 3 path as a subgraph of this of the target graph that you have plugged in. And this is generally true for every matrix symmetric polynomial. And so then I thought, I contacted Tim Seppelt, who is an expert in homomorphism and subgraph counting, and I asked him what he could make of this.
Yeah, Benedikt contacted me asking about the complexity of these subgraph polynomials. And what I thought at first is that, okay, subgraph polynomials are best understood via so-called homomorphism polynomials. So homomorphism polynomials are very similar to subgraph polynomials. The only difference is that we don't impose this injectivity condition. So if you look at this expression here, so this is the subgraph polynomial of the 3 path. This is what Benedikt showed you on the last slide. And the crucial point here is highlighted in red below. So we sum over all possible images of this 3 path. And the point is that the 2 variables I1 and I2 that indicate where the outer two vertices of the paths are mapped to are distinct. So this makes it a subgraph rather than an arbitrary mapping into an n by n bipartite graph. Another point is that subgraph polynomials can be written as linear combinations of homomorphism polynomials. And that's quite easily seen in this example here. So by a homomorphism polynomial, I now mean a polynomial where we don't impose these non-equal conditions that there was here in red. So the subgraph polynomial of the 3-path is a linear combination of two homomorphism polynomials, namely the homomorphism polynomial of the 3-path. This is the first term where we just drop the non-equal condition. And then the homomorphism polynomial of this double-edge 1-path. And this comes from the fact that if we take the sum over all of these terms in the first summand, then we have to subtract all the terms where the two outer vertices are mapped to the same vertex, and this is precisely the homomorphism count from this double-edged 2-path. Okay, so just to recall the observation that Benedikt made on the last slide, matrix symmetric polynomials are the same as linear combinations of subgraph polynomials. So every matrix symmetric polynomial can be written as a linear combination of subgraph polynomials. And now what we saw on this slide is that subgraph polynomials are actually the same thing as linear combinations of subgraph polynomials are the same thing as linear combinations of homomorphism polynomials. And this transformation that we've seen is called the Möbius transformation or Möbius inversion. So now what we see here are 3 equivalent characterizations for the same set of polynomials. And why are homomorphism polynomials somehow more useful than subgraph polynomials, at least in this case? This is because this setup in which we are reminded me a lot of this result here by Kurtikapian, Dell, and Marx from Stock 2017, I think, who proved a complexity dichotomy for evaluating linear combinations of homomorphism counts. So this is not in the algebraic complexity setting, but in a general parametrized counting complexity setting. So this theorem here says that such a graph motive parameter, so this is a linear combination of homomorphism counts from some pattern graphs F with coefficients alpha F, can be evaluated in fixed in FPT time if and only if all the patterns in this linear combination have bounded tree width. And remember, we wanted to prove some complexity criterion for matrix symmetric polynomials. We saw that all of them are linear combinations of homomorphism polynomials. So is there maybe a similar statement in the algebraic world as well? And this is precisely what we proved. So this is our main theorem. We show that for a sequence of matrix symmetric polynomials Pn, the following two things are equivalent. The polynomials admit symmetric circuits of polynomial size. Let's skip over this orbit size aspect. So think of this as being polynomial size, if and only if the polynomials can be written as linear combinations of homomorphism polynomials for pattern graphs of bounded tree width. So at first, this theorem looks very similar to the theorem on the top, and in a way, our working hypothesis turned out to be right.
But for reasons which are totally different than in the Kurtikapian Del Marx paper. So the proof technique is an original one and has nothing to do with this other result. One direction of this theorem is essentially standard and pretty much known.
So you mean expressing homomorphism polynomials of bounded tree width patterns using small symmetric circuits?
Yes. So this can be done by building up the homomorphism count inductively along the tree decomposition of the pattern graph F, which can also be done symmetrically. And I think this is a known trick from the homomorphism counting literature.
Yes, this is fairly standard, and as far as I know, this idea appeared first in a paper by Flum and Grohe in 2004.
Yeah, but the backwards direction of the theorem, so going from 1 to 2, so starting with a symmetric circuit and proving that it computes bounded tree with homomorphism counts, that's actually much more technical, and that's basically the original part of our work. And I remember we only managed to do this on the last day of Tim's visit to Cambridge. Basically what we did is to compute, or to show inductively that for every gate in the circuit really computes something like a linear combination of homomorphism counts of bounded tree width. And crucially, the tree width is linked to the exponent of the circuit size. And this can be shown with an inductive calculation.
Yeah, but the actual calculations are rather involved and lengthy, so we can't unfortunately go into detail here.
But we should perhaps mention another thing. Apart from the proof techniques, there's another important difference between what we did and the results of Kurtikapian, and Marx. And we only noticed this halfway through the project. And that's that our whole setup is non-uniform, which is not typically what's done in this related literature.
Exactly. So by non-uniformity, we mean that the linear combinations of homomorphism polynomials that we evaluate may depend on the graph size we evaluate them in. So there's one linear combination for every graph size in this infinite family. And in this result by Kurtikapian, Dell, and Marx, what they study are linear combinations of homomorphism polynomials that can be evaluated at an arbitrary host graph size. And this has a significant, a crucial technical effect, namely that, for example, the linear combinations that we are considering are no longer unique. So there might be several linear combinations for the same parameter.
And I remember we struggled in particular to understand the case where the size of the pattern graph is linear in the size of the target graph. So basically, when the pattern graph is as large as the target graph that you're counting it in. That seems to be the regime that where many results, or many of the side results we're not talking about here in this presentation, seem to fail.
Yes, that seems to be really a very wild territory, the territory of linear size pattern graphs. And this is where very unexpected and mysterious things happen that we still need to uncover.
But to come back to the beginning of the story, so before we got into this whole homomorphism and subgraph counting story, the original goal was proving new lower bounds for symmetric circuits for polynomials other than the permanent. So have we come any closer to this goal?
So we have definitely developed a very useful theoretical framework for thinking about this. And this bounded tree width criterion fully answers the question for which polynomials admit such lower bounds. But actually proving that a certain family of polynomials does not admit small tree width linear homomorphism polynomial combinations is quite difficult, and to the best of our knowledge, the only way of actually doing this is using similar techniques to what Anuj and Greg used in their unconditional lower bounds for symmetric circuits for the permanent.
Yeah, and what you mean there is the connection to counting width or Weisweiler-Riemann dimension. So let me say a little bit about this. So for paragraphs G and H, we say that they're K-equivalent if they're not distinguished by the K-dimensional Weisweiler-Riemann approximation of isomorphism. I'm not going to get into a definition. But this leads us to a notion of a counting width of a graph parameter. So a graph parameter nu is any function from graphs to numbers. And its counting width is the function which gives us for each n the smallest value so that this nu is constant on each kn equivalence class of n vertex graphs. Well, if this function kn is unbounded, and we know that any graph parameter of unbounded counting width cannot be computed by symmetric Boolean circuits of polynomial size. And necessarily, this means that algebraic circuits which compute a family of polynomials, where evaluating the polynomial gives you this graph parameter, must also be of superpolynomial size. So this connection between counting width and circuit complexity was established in prior work. And I think it's worth mentioning, it's not on the slide, is Dvorak's result, which characterizes k-dimensional Weisweiler-Riemann equivalence in terms of homomorphism counts from graphs of bounded tree width, which connects it back to the thing we're studying. To wrap up, we've connected all sorts of different complexity measures: symmetric circuit size, tree width of homomorphism polynomials, counting width of graph parameters. All of these things gel together into a rather beautiful theory of symmetric circuit computation.
Yes, and this works out especially nicely in the case where these pattern graphs F that we're counting are of sublinear size compared to the target graph. Then we've really shown that all these three complexity measures are completely aligned.
Yes, but as you already noted, for linear size patterns, we have examples showing that the picture cannot be as neat as it is here. So this requires further investigation. So
what's on the agenda for the future?
Ultimately, it would be nice if we could really use this symmetric circuit theory to also make progress in understanding the power of general non-symmetric circuits. So intuitively, what our main result is saying is that if we consider only matrix symmetric polynomials, then the only examples where non-symmetric circuits could really be stronger than symmetric ones are homomorphism polynomials where the tree width is non-constant.
Because if the tree width is bounded, then they're easy both for symmetric and non-symmetric circuits.
Exactly. We only have symmetric hardness in the case of growing tree width, so it would be interesting to see how non-symmetric circuits perform for these types of polynomials.
And if also the non-symmetric circuits should require superpolynomial size for these, then this would mean that symmetric and non-symmetric circuits really have the same power, at least for matrix symmetric polynomials.
That would seem surprising, but maybe it's true at least for certain classes of polynomials.
We can hopefully tell you the answer in our next video.
Thank you very much.